In the first infinitesimal fraction of a second after the Big Bang, something extraordinary happened. The entire universe, all of space itself, expanded faster than light could possibly travel. It was a moment of cosmic rebellion, when the rules we thought were absolute simply didn't apply. And that paradox, that impossible moment, has haunted physicists ever since. Because if the universe could do it, why can't we? Why can't anything else? Einstein declared light speed the cosmic speed limit, the ultimate boundary that nothing can cross. Yet for over a century, brilliant minds have searched for loopholes, workarounds, hidden passages through spacetime. Some have found phenomena so strange, so counterintuitive, that they seem to bend the very rules of reality itself. So here's the question that will guide us through the next 3 hours together. Is anything actually faster than light? Or is light speed something far more profound, not just a limit, but a fundamental truth woven into the fabric of existence itself? I'm so glad you're here. If you find yourself wondering about the cosmos, if you want to explore the deepest mysteries of physics with curiosity rather than equations, please like this video and subscribe. Your thoughts matter. Share them in the comments below. Now, let's begin our journey into one of the universe's greatest secrets. The cosmic speed limit. Think about the fastest thing you've ever seen. Maybe it was a jet plane screaming across the sky, or lightning splitting a dark cloud in two, or perhaps a moment when time felt like it was moving impossibly fast. Now imagine something that's about 1,000,000 times faster than all of those combined. That's light. And for nearly 4 centuries, it's been the measuring stick by which we understand speed itself. But here's where it gets interesting. Light isn't just fast. Light is the fastest. It's the cosmic speed limit, the ultimate boundary that the universe refuses to let anything cross. And that single fact has shaped everything we know about reality. When we look at the night sky, we're not just looking at stars. We're looking backward through time itself, watching light that left distant suns hundreds of years ago finally reaching our eyes. When we use GPS to find our way, we're relying on the constancy of light speed. When we understand that time doesn't flow the same for everyone, that gravity bends space, that matter and energy are interchangeable, we're all following clues that Einstein left for us. Clues that begin with one simple, revolutionary idea. The speed of light is always the same, no matter who measures it or from where they measure it. It sounds simple, almost mundane. But this single fact rewrote physics, transformed our understanding of time itself, and created a mystery that still captivates brilliant minds today. Because if light speed is truly the cosmic speed limit, why does the universe seem so determined to break it? The dream of the impossible. We've always wanted to go faster. It's written into our nature as curious creatures. Before we could fly, we dreamed of flight. Before we could travel underwater, we imagined submarines. And long before we could even approach the speed of light, we fantasized about surpassing it. In the early 20th century, when science fiction was still finding its voice, writers imagined spaceships that could zip between stars as easily as a car drives between cities. They didn't imagine the constraints that Einstein would soon impose on us. They didn't know that relativity would make faster-than-light travel seem not just difficult, but fundamentally impossible. But here's the beautiful thing about the human mind. Impossibility has never really stopped us from dreaming. If anything, it makes us dream harder. So physicists started asking, if we can't go faster than light, could we at least find a loophole? Could there be something we're missing, some hidden pathway through the laws of nature? And this question, this persistent, almost stubborn refusal to accept limitation, has become one of the most fruitful obsessions in modern physics. Think about it from their perspective. These are people trained to question everything, to look for exceptions, to find the cracks in every system. You give them an absolute rule, and their first instinct is to test it, probe it, see if maybe, just maybe, reality is stranger and more flexible than we thought. Sometimes they find nothing but confirmation of what Einstein already knew. But sometimes they find something so strange, so unexpected, that it challenges everything we thought we understood. Quantum tunneling, cosmic inflation, entanglement. Phenomena that seem to mock the speed limit, that seem to operate in defiance of light's supremacy. And that's what draws physicists back again and again, like explorers searching for a passage through an impossible mountain. What if the loophole is real? What if there's something faster than light hiding in the shadows of quantum mechanics, or written into the very expansion of the universe itself? What faster actually means? Before we can even ask whether anything is faster than light, we need to stop and ask ourselves a more fundamental question. What does faster actually mean? It sounds obvious, doesn't it? Faster means you cover more distance in less time. A car going 60 miles per hour is faster than a bicycle going 10 miles per hour. Simple. But the moment you start talking about the speed of light and the structure of the universe itself, things get delightfully complicated. You see, speed depends on perspective. Imagine you're on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour. From the ground, that ball is moving at 80 miles per hour. But from your seat on the train, it's moving at 20. The speed is relative. It depends on who's measuring and from where they're measuring. This might seem like a small technicality, but Einstein took this idea and ran with it into regions of physics that no one had ever explored before. He asked, what if the same relativity applies to light? What if light speed is always measured as the same speed, no matter who's doing the measuring or how fast they're moving? The answer to that question cracked open the entire structure of spacetime. But it also means that when we talk about something being faster than light, we have to be very careful about what we mean. Are we talking about something moving faster through space? Or are we talking about the expansion of space itself? Are we talking about information traveling from point A to point B? Or are we talking about something that appears to move faster, but isn't actually moving at all? Because here's a curious fact. The universe expanding faster than light during inflation wasn't actually violating relativity. Nothing was moving faster than light relative to anything nearby. Space itself was simply growing, and Einstein's rules didn't apply to the expansion of space itself. They applied to how fast things could move through space. It's a subtle distinction, but it's crucial. And as we journey through this question together, you'll see how these subtle distinctions matter enormously. The universe, it turns out, is far more nuanced than simple rules allow. A universe of contradictions. So here we are, at the threshold of a great mystery. We have rules that seem absolute, written into the fabric of reality itself. And yet the universe keeps presenting us with phenomena that seem to contradict those rules. Let me tell you about a few of them, just to whet your appetite for what's coming. Imagine a particle trapped behind an energy barrier so high that, according to classical physics, it should never escape. And yet, somehow, it does. It appears on the other side of the barrier as if it walked straight through an impossible wall. Physicists call this quantum tunneling, and it happens constantly at the quantum scale. The particle doesn't travel faster than light to get through, but it does cross the barrier instantaneously, in zero time. How is that possible? Or consider this. Two particles become entangled, and then you separate them across the universe. You measure one particle, and instantly, the other one responds, as if they're communicating faster than light could possibly travel. Einstein called this spooky action at a distance, and he was deeply troubled by it. He thought there must be something hidden, something we were missing. But experiments have repeatedly confirmed that it's real. So how does that work without violating relativity? Then there's the expansion of the universe itself. Galaxies far away from us are receding so fast that the space between us and them is expanding faster than light. We can actually measure it. We can see distant galaxies moving away from us at speeds greater than light speed. But Einstein said nothing can move faster than light, So how is this possible? And finally, in the earliest moments after the Big Bang, the entire universe inflated at an impossible rate. Space itself expanded faster than light in every direction. It was the ultimate cosmic speed violation. And yet, it didn't break the rules. It couldn't have, because the rules themselves were written into the fabric of that expanding space. So we're left with this strange situation. We have what appears to be several violations of the cosmic speed limit, and yet relativity stands as one of the most tested and confirmed theories in all of science. Which means the violation isn't real, or our understanding of what the violation means needs to be much more sophisticated. And that's exactly what we're going to explore together. Not with equations and technical jargon, but as a genuine mystery unfolding before us. The universe seems to be playing tricks on us, hiding secrets in plain sight. And our job, over these next 3 hours, is to understand what those secrets are really telling us about the nature of reality itself. Before the storm, imagine standing at the end of the 19th century, looking at physics through the eyes of a confident scientist. The world felt knowable. Newton's laws explained how objects moved through space. Maxwell's equations described how light and electricity worked. Gravity was understood. The universe seemed like a great machine, precise and predictable, ticking along according to immutable rules. There was even a substance called the ether, an invisible medium that filled all of space, through which light waves traveled like ripples on an ocean. Serious physicists believed in the ether. It made sense. Waves need something to wave through after all. Sound needs air. Water waves need water. So light must need the ether. And if the ether existed, then it should be possible to measure how fast the Earth was moving through it. Imagine the ether as a cosmic wind. If you're moving through wind, you can detect it. You feel it. It slows you down in one direction and speeds you up in another. So in 1887, two brilliant experimenters named Albert Michelson and Edward Morley decided to do something elegant. They built an instrument sensitive enough to detect Earth's motion through the ether. They pointed it in one direction, then rotated it 90 degrees and pointed it at right angles. If the ether was real, if there was a cosmic wind, they should see a difference. They should detect Earth's motion through space. They performed the experiment with meticulous care, and they got nothing. No difference. No cosmic wind. No sign of Earth's motion through the ether. It was the experiment that broke an era. They were measuring the speed of light in different directions, and it was always the same. This result puzzled physicists for years. How could light always travel at the same speed, no matter which direction you measured it? How could there be no ether if light waves needed something to travel through? It violated everything they thought they understood about how waves worked. But instead of dismissing the result as an experimental error, physicists sat with the puzzle. They measured it again and again, refining their instruments, expecting someday to detect that cosmic wind. But it never came. The universe was keeping a secret, and the greatest minds of the age were stumbling around in the dark, not quite understanding what the secret was trying to tell them. They were close to a revelation. They just didn't know it yet. The young patent clerk's insight. In 1905, a young man named Albert Einstein was working as a patent clerk in Bern, Switzerland. He wasn't a famous physicist. He hadn't even finished his doctorate, but he had something more valuable than credentials. He had an extraordinary capacity to think clearly about the deepest problems in physics. And he was thinking about light. Einstein knew about the Michelson-Morley experiment. He knew that light speed seemed to be constant, regardless of how you measured it. But instead of being puzzled by this, instead of trying to explain it away, he asked a radically different question. What if the Michelson-Morley result wasn't telling us that the ether must exist? What if it was telling us something far more profound? What if light speed is truly constant? What if it's not the ether that's fundamental, but light itself? This might sound like a subtle shift in thinking, but it was revolutionary. Because if light speed is always the same, no matter who measures it or how fast they're moving, then something else has to give. And Einstein realized what that something was: time and space themselves. Here's a thought experiment to understand what he meant. Imagine you're on a moving train and you bounce a light beam from the front of the car to the back. From your perspective on the train, the light travels at light speed. Now imagine someone standing on the platform watching the train zoom past. If they measure how fast that same light beam is traveling, they should measure a different speed, right? The light is moving forward with the train, so it should be faster. But according to the Michelson-Morley experiment, they don't measure a different speed. They measure the same speed. Light is traveling at the same speed from their perspective too. How is that possible? The only way it's possible is if time itself is running at different rates on the train and on the platform. Time isn't absolute. It's relative. It depends on how fast you're moving. Einstein realized something even more radical. If time isn't absolute, then simultaneity isn't absolute either. Two events that happen at the same time for someone on the train might happen at different times for someone on the platform. The concept of now becomes fuzzy, relative, dependent on the observer. This wasn't just a small adjustment to Newton's physics. This was a complete reimagining of the structure of reality. And from this single insight, that light speed is constant. Everything else followed like dominoes falling: length contraction, time dilation, mass-energy equivalence, the curvature of spacetime. A new physics that would dominate the 20th century and reshape how we understand the universe. All from a young man in a patent office asking the right question. Time is not absolute. Let's sit with this idea for a moment, because it's so counterintuitive that it deserves to sink in slowly. Time, as you experience it, feels absolute. Right now, at this very moment, you're living in the present. The past is behind you. The future is ahead. And everyone else in the world, as far as you can tell, is living in that same present moment. We're all in the now together. Except we're not. Not really. Not according to Einstein. And not according to every experiment that's tested his theory. Here's where it gets strange. Imagine you have a twin, and on their 21st birthday, they board a spaceship that travels at 90% the speed of light. They zoom away from Earth for 5 years, and then turn around and come back. From your perspective on Earth, 10 years have passed. You're 31 years old. But your twin, according to relativity, your twin has barely aged. Maybe they're only 26 years old. They've experienced less time than you have. This isn't science fiction. This is a real prediction of relativity, and we've actually measured it. We've sent atomic clocks on airplanes, flown them around the Earth, and brought them back. The clocks that flew on the planes showed less time had passed than the stationary clocks on the ground. It's tiny, we're talking nanoseconds, but it's real. Time literally passes at different rates depending on how fast you're moving. And here's the part that connects to our central mystery. The closer you get to the speed of light, the more dramatic this effect becomes. As you approach light speed, time slows down more and more. If you could actually reach light speed, which you can't, time would stop completely. This also means that simultaneity, the concept of now, becomes relative. Two events that happen at the same time for you might happen at different times for someone moving at a different speed. There's no universal now ticking across the cosmos. There's only local nows, relative to each observer's motion through space. Physicists visualize this with something called a space-time diagram. Instead of just thinking about space and time separately, they think of them as woven together into a single four-dimensional fabric. And light travels along the boundary of what's possible in that fabric. Everything else is confined to move slower than light, creating a kind of cosmic boundary that nothing can cross. When you understand time this way, not as a river flowing from past to future, but as a dimension woven into the fabric of reality alongside space, you begin to understand why light speed is so special. It's not just a speed limit. It's a fundamental feature of the structure of spacetime itself, and that's why nothing that has mass can ever reach it. Space bends too. If time isn't absolute, then neither is space. This is where Einstein's thinking becomes even more dizzying. We tend to think of space as a fixed stage on which events occur, a three-dimensional backdrop. But Einstein realized that space is just as flexible as time. It contracts, it warps, and in doing so, it enforces the cosmic speed limit in a way that's almost elegant. Imagine you're traveling toward the speed of light. From the perspective of someone watching you, something strange happens. You don't just slow down in time, you also get shorter. In the direction of your motion, you contract. Not in the psychological sense. Not because you're being squeezed. You actually get compressed. If you were traveling at 90% the speed of light, someone watching you would see you compressed to about 44% of your normal length. From your perspective inside the spaceship, everything feels fine. You haven't changed. But from the external observer's perspective, you've been squashed like a pancake. This isn't an illusion or a trick of the light. It's how space itself behaves at relativistic speeds. And here's the profound part. These contractions, time dilation and length contraction, work together perfectly to enforce the cosmic speed limit. Let's say you wanted to accelerate to light speed. You have a powerful rocket and you start accelerating. As you get faster, something happens. From the external observer's perspective, your rocket gets shorter and shorter. Your clocks tick slower and slower. And something else happens too. You get heavier. Your inertial mass increases. It takes more and more energy to push you faster. The closer you get to light speed, the more energy it requires. At light speed, it would require infinite energy. It's impossible. You can never actually reach light speed if you have mass. But that's not the only way space enforces the cosmic speed limit. Imagine you wanted to take a shortcut. You wanted to warp space itself, to create a tunnel through spacetime that would let you bypass the normal rules. You create a wormhole. You bend space so dramatically that the distance between 2 points becomes zero. Theoretically, you could step through and arrive at a distant location instantly. But here's the problem. To create such a wormhole, you'd need negative energy. You'd need something that has negative mass, something that repels rather than attracts. And as far as we know, such exotic matter doesn't exist in any quantities that could actually be useful. Space itself seems to be arranged in such a way that shortcuts are impossible. The universe is sealed. It protects its speed limit. And the more we try to understand how it does this, the more we realize we're not looking at arbitrary rules. We're looking at fundamental principles woven into the structure of reality itself. The price of acceleration. So let's talk about the practical reality of approaching light speed. If you wanted to get close to it, say 95%, what would it actually take? This is where the mathematics of relativity becomes viscerally real. To accelerate an object of normal mass to 95% light speed would require a staggering amount of energy. We're talking about energy equivalent to millions of nuclear weapons. For a spacecraft with a crew, we'd be talking about energy equivalent to billions of nuclear weapons. And that's just to get it to 95%. To get closer and closer to light speed, the energy requirements grow exponentially. To reach 99% light speed would require 10 times more energy. To reach 99.9% would require 100 times more. It's a mathematical war. The closer you get, the steeper the cost becomes. Think about it this way. We have spacecraft that have left the solar system. The fastest one, Parker Solar Probe, moves at about 135 miles per second. Light moves at 186,000 miles per second. Our fastest spacecraft is moving at about 0.07% the speed of light. To reach even 1% of light speed, we'd need to increase our velocity by more than 1,000 times. It's not a matter of building a better rocket. It's a matter of physics itself becoming your opponent. And as you approach light speed, physics puts up an increasingly impassable wall. This is where the cosmic speed limit becomes something truly profound. It's not just a rule. It's a consequence of how energy, mass, and the structure of space and time are woven together. You can't break it, because to break it would require infinite energy. And the universe doesn't have infinite energy to give. Every star, every galaxy, every bit of matter and energy in the observable universe wouldn't have enough to accelerate a single gram to light speed. The universe itself seems designed to prevent it. And this raises a profound question. Is the universe protecting causality? Is it preventing time paradoxes? Is it maintaining the fundamental order of reality? Or is light speed simply a mathematical consequence of how space and time are fundamentally structured? These questions will guide us as we explore what the universe might be hiding. Because even if nothing can travel faster than light through space, that doesn't mean the universe has no secrets left to reveal. It just means the secrets are far stranger than we ever imagined. Where rules break down. Everything we've explored so far comes from relativity, from Einstein's grand vision of how space and time are woven together. And relativity is extraordinarily successful. It explains planets orbiting stars. It explains black holes. It explains gravity itself as the curvature of spacetime. But there's a problem. When physicists tried to apply relativity to the realm of the very small, to atoms and electrons and particles of light, things started getting weird. Not just weird in the way that relativity is counterintuitive, weird in a way that seems to violate the very logic of how the universe should work. And this is where quantum mechanics comes in. The quantum realm operates by different rules. Or perhaps it would be more accurate to say it operates by rules that are so strange, they seem like no rules at all. Let me give you a sense of what I mean. In the quantum realm, particles don't have definite properties until you measure them. An electron doesn't have a specific position. It exists in a kind of cloud of probability. It's everywhere and nowhere at once until the moment you look at it. And the instant you look, the cloud collapses. The electron is suddenly somewhere specific. But if you don't measure where it is, it genuinely doesn't have a location. This isn't about our knowledge. This isn't about instruments that aren't precise enough. It's about the fundamental nature of reality. The universe, at its deepest level, is built on probability and uncertainty, not on definite facts. And this realm of uncertainty is also where we find some of the strangest challenges to the cosmic speed limit. At the quantum level, things happen that seem impossible according to classical logic. Particles tunnel through barriers. Information appears to travel faster than light. Measurements made in one location instantly affect measurements in another location across the universe. All of this happens in a realm where Einstein's rules should still apply. And yet they seem to be bent, twisted, tested in ways that make physicists scratch their heads and ask fundamental questions about what reality actually is. Now, here's the thing. When physicists discovered these phenomena, they didn't immediately think, "Oh, Einstein was wrong." Instead, they realized something subtler. The quantum realm doesn't violate relativity. It's far too weird for something that's simple. Instead, it reveals that there are loopholes in how we think about the universe. Not loopholes in relativity itself, but loopholes in how we interpret what relativity means. These loopholes are subtle and profound. They touch on the nature of causality itself. They raise questions about whether information and influence are really the same thing. They force us to reconsider what we mean by nothing can move faster than light. Because in the quantum realm, some things move faster than light. They just don't move in a way that allows you to send information faster than light. They move in ways that don't violate causality, that don't create paradoxes, that somehow preserve the fundamental logic of the universe, even as they seem to violate its rules. This is where our mystery deepens. This is where the universe starts to reveal that it's far more clever than we gave it credit for. And as we explore these quantum phenomena, we'll start to understand that the cosmic speed limit isn't just a hard ceiling. It's a reflection of something much deeper about how reality is structured. It's a protection mechanism. It's a statement about causality and information and the fundamental nature of time itself. Tunneling through walls. Imagine you're in a room with a thick concrete wall. The wall is solid. You can't walk through it. An ordinary baseball thrown at the wall will bounce off. But in the quantum realm, imagine an electron approaching that wall. According to classical physics, the electron should bounce off just like the baseball. The wall is an energy barrier. The electron doesn't have enough energy to cross it, so it shouldn't be able to cross. And yet, sometimes it does. The electron appears on the other side of the wall as if it walked straight through. And here's the really strange part. It does this instantaneously. It doesn't take time to cross the wall. One moment, it's on one side. The next moment, it's on the other. There's no moment in between where it's crossing. This phenomenon is called quantum tunneling, and it's not a metaphor. It's a real, measurable, reproducible aspect of how particles behave. We observe it in laboratories all the time. We've built technologies that depend on it. Flash memory in your phone uses quantum tunneling. Certain types of microscopes are based on tunneling. Without quantum tunneling, modern electronics wouldn't exist. So what's happening? How is a particle crossing a barrier that it doesn't have the energy to cross? The explanation lies in the probabilistic nature of quantum mechanics. At the quantum level, particles don't have definite positions. They exist as a wave of probability. And this wave of probability extends slightly into the barrier. Most of the wave bounces off, but a small part of it penetrates through the wall. And there's a small probability that when you measure the particle, you'll find it on the other side of the barrier. The smaller the barrier and the lighter the particle, the higher that probability becomes. It's as if the universe is playing a game of chance with us. The particle rolls the dice. Most of the time, it loses and stays on the original side. But sometimes, probability favors it, and it wins. It appears on the other side. Now, here's where this connects to our central question about the speed of light. Tunneling seems to involve instantaneous travel. The particle doesn't traverse the barrier at light speed or slower. It's simply on one side, then it's on the other. No time passes. Doesn't this violate the cosmic speed limit? Doesn't this mean that something can move faster than light? The answer is subtle and beautiful. The particle itself, technically, isn't moving faster than light. It's not moving through space at all. It's not traveling. Instead, it's taking advantage of the quantum uncertainty principle. For an infinitesimal moment, the universe allows the particle to exist in a superposition. It's somewhere in a fuzzy cloud of probability. Then the cloud collapses. The measurement pinpoints its location. And yes, it might be on the other side of the barrier. But no information traveled faster than light. You had to wait for the electron to tunnel through. And once it's on the other side, you have to measure it to know it's there. You can't use tunneling to send a message faster than light. You can't cause an effect faster than light. You can only observe this strange probabilistic behavior, and that observation by itself doesn't violate the laws of physics. Instead, it reveals that the laws are far subtler than we initially thought. Spooky action at a distance. Einstein hated this. He genuinely did not like what quantum mechanics was telling him about the universe. And of all the things in quantum mechanics that bothered him, none bothered him more than entanglement. Imagine you have two particles that are quantum entangled. They were created together, or they interacted in a way that linked them. And then you separate them. You send one to Tokyo. You keep the other in New York. They're on opposite sides of the planet, separated by thousands of miles. And then something remarkable happens. You measure the first particle. You look at one of its properties, and at that instant, the second particle, thousands of miles away, responds. Its properties shift. Its state changes. It's as if the two particles are communicating instantly, faster than light could possibly carry a message. Einstein, in 1935, called this spooky action at a distance. He found it deeply troubling. He believed there must be something hidden, some variable that both particles knew about that determined how they would respond when measured. He believed that once the particles were separated, no communication between them could affect how each one measured. But in 1964, a physicist named John Bell proved something extraordinary. Bell showed that if hidden variables existed, if the universe really worked the way Einstein wanted it to work, then certain measurements must correlate in very specific ways. He created an inequality that, if violated, would prove that hidden variables don't exist. If hidden variables don't exist, then either particles are communicating faster than light, or the very concept of local reality is broken. For decades, physicists tested Bell's inequality, and experiment after experiment showed that it's violated. The correlations between entangled particles are stronger than any hidden variable theory could predict. The universe is truly strange. Entangled particles really do respond to each other instantaneously across any distance. Now, you might think this proves that faster-than-light communication is possible. You might think we've finally found our loophole. You might think that entanglement allows us to send messages faster than light. But here's the crucial part. You can't. And here's why. When you measure the first particle, the result is random. You get a random outcome. And the second particle's measurement, influenced by your measurement, also appears random to whoever is measuring the second particle. The correlation is there, but it's hidden in the randomness. To see the correlation, to prove that your measurement affected the distant particle, you'd have to communicate the results of your measurement to the person measuring the distant particle. And that communication travels at light speed or slower. You can't use entanglement to send information. You can only use it to create correlations that are impossible to explain with local hidden variables. Physicists call this non-locality, and it's deeply unsettling. It means that quantum mechanics is fundamentally non-local. Measurements in one place can instantaneously affect reality in another place. And yet, somehow, this doesn't allow faster-than-light communication. The universe has figured out a way to have its cake and eat it too. It allows instantaneous correlations while still preserving the cosmic speed limit on information transfer. It's one of the deepest mysteries in physics, and it forces us to ask, what does locality even mean? What does it mean to say that objects are separate if a measurement on one instantly affects the other? Information versus influence. Here's a distinction that might seem subtle, but it's absolutely crucial to understanding why quantum mechanics doesn't break the cosmic speed limit. It's the difference between influence and information. Let me explain what I mean. When you measure an entangled particle in New York, your measurement influences a particle in Tokyo. That's real. That influence is instantaneous. It's non-local. But here's the key. That influence doesn't carry information from New York to Tokyo. It doesn't send a message. It doesn't allow you to control what happens in Tokyo. Let's use an analogy. Imagine you and a friend each have a magic coin. You flip your coin in New York. The moment you flip it, the coin in Tokyo falls to the ground and lands on the same side yours did. Heads if yours is heads, tails if yours is tails. Your flip influenced the distant coin instantaneously. But did you send information to Tokyo? Did you communicate anything useful? Not really. From the perspective of someone in Tokyo, the coin just randomly landed on a side. They don't know that your flip happened. They don't know that your coin matched theirs. To find out, they'd have to call New York and ask what your coin showed. And that phone call travels at the speed of light or slower. So yes, there's influence. Yes, there's non-locality. But no, there's no faster-than-light communication. This is the resolution to the paradox. This is how quantum mechanics preserves causality even while allowing instantaneous correlations. The universe has found a way to allow non-local influence while preventing non-local communication. And this distinction between influence and information is at the heart of understanding why nothing can actually exceed light speed in any meaningful sense. You see, the cosmic speed limit isn't really about speed. It's about causality. It's about information flow. It's about the ability to cause effects. Causality requires information. You can't influence something you don't have information about. You can't cause an effect at a distance unless you send some kind of signal or influence that carries meaning. And all meaningful signals, all carriers of information, travel at or below light speed. This is why we can have instantaneous correlations in quantum mechanics. This is why particles can influence each other across the universe at light speed. But we still can't send messages faster than light. We still can't create a timeline paradox. We still can't have an effect that precedes its cause. Because information, meaningful information that could create causality problems, always travels at or below light speed. And as long as that's true, the cosmic speed limit is preserved. The universe is protected from paradox. And reality remains logically consistent, even in the face of quantum weirdness. Virtual particles and borrowed time. There's another way that quantum mechanics seems to bend the rules, and it's even stranger than entanglement. It involves something called virtual particles. And to understand them, we have to talk about one of the most fundamental principles in quantum mechanics, the Heisenberg uncertainty principle. Werner Heisenberg discovered something profound. At the quantum level, there's a fundamental uncertainty built into the fabric of reality. You can't simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you know where a particle is, the less precisely you know how fast it's moving, and vice versa. There's a trade-off. It's not a limitation of our instruments. It's a fundamental limit on what the universe allows. But there's another version of this uncertainty principle that's even more relevant to our story. At the quantum level, there's an uncertainty in energy and time. Just like you can't know both position and momentum perfectly, you can't know both energy and time perfectly. And here's where it gets mind-bending. The universe allows you to violate energy conservation for a brief moment, as long as you give that energy back quickly enough. It's like the universe is borrowing money from the future, and it has to pay it back before anyone notices. For infinitesimal moments, particles can pop into existence out of nothing. An electron and its antimatter counterpart, a positron, can appear from the vacuum. They exist for a brief instant. They interact with other particles, and then they annihilate each other, returning the borrowed energy to the universe. These are virtual particles. They're not real in the sense that you can measure them directly. They're ephemeral ghosts that flicker in and out of existence constantly. And according to quantum field theory, they're everywhere, all the time, popping into and out of existence at rates that would make your head spin. Now, here's the strange part. These virtual particles are constantly interacting with the real particles around them. They affect the behavior of electrons. They influence how charged particles interact. We can measure their effects. We can see the traces they leave. And in a very real sense, they're mediating the fundamental forces of nature. But here's where our central question comes in. Virtual particles appear instantaneously. They exist for zero time in a sense. They violate energy conservation, even if only for an infinitesimal instant. Doesn't this mean that something is exceeding the cosmic speed limit? Doesn't this mean that something is traveling faster than light? The answer, again, is subtle. Virtual particles don't violate relativity because they're not real particles. They're not things that exist in a way you can measure or control. You can't use them to send information. You can't cause an effect faster than light with them. They're part of the mathematical formalism that physicists use to calculate how real particles interact. They're useful fictions, mathematical conveniences that help us understand how the universe works. But they're not physical objects that can be controlled or observed or used as a means of faster-than-light communication. And that's the key. Over and over, in quantum mechanics, we see phenomena that seem to violate relativity. Tunneling, entanglement, virtual particles. But none of them allow faster-than-light communication. None of them break causality. None of them create paradoxes. Instead, they reveal that relativity is more subtle than we thought. The cosmic speed limit isn't just a rule about how fast you can move. It's a deep truth about information, causality, and the nature of influence itself. And the quantum realm, as strange as it is, ultimately respects that truth. Light's competitors in empty space. We've spent a lot of time talking about why nothing can move faster than light. We've explored the mathematical reasons, the physical constraints, the way the universe seems to protect this speed limit like a sentinel guarding the only gate through the cosmic castle. But now I want to shift perspective. I want to ask a different question. In the vast emptiness of space, traveling from star to star, crossing the immense distances between galaxies, what actually moves through the void? Light, obviously, but what else? This might sound like a strange question. You might think, well, nothing moves faster than light, so light is the speed record holder by default. But the universe is far more interesting than that. There are things that travel through space. Some of them move slowly. Some move at remarkable speeds. And some of them seem, at first glance, to be moving faster than light itself. One of the most fascinating things that travels through the universe is gravity. For centuries, physicists debated whether gravity was instantaneous. Newton thought it was. He couldn't explain how, but his equations worked as if gravity reached across space instantaneously. The moment the moon moved, gravity's influence on Earth changed. No delay, no time lag. Just instant connection. But Einstein showed that gravity isn't instantaneous. It's the curvature of spacetime, and that curvature propagates at light speed. Gravity waves travel through space like ripples on a pond, and they move at exactly the speed of light. We've detected these gravitational waves now. We've measured them, and they confirm what Einstein predicted more than a century ago. Gravity travels at light speed. Then there are particles. Photons, of course, move at light speed. But there are other particles that move slower. Electrons, neutrinos, protons. All of them are constrained by relativity. All of them are limited to speeds below light speed. But here's where it gets interesting. There are things moving through space that aren't particles in the traditional sense. There are fields, quantum fields that permeate all of space, and they propagate at light speed. There are waves of electromagnetic energy. There are sound waves traveling through the interstellar medium, though infinitesimally slow compared to light. And then there are the truly exotic competitors. The things that don't fit neatly into our categories. The things that challenge our understanding of what faster than light even means. As we explore the cosmic speed records, we'll discover that the universe isn't as simple as light being the fastest thing. Instead, light is the fastest thing that carries information. Light is the fastest thing that can cause effects, that can influence distant events. And that might be the real secret. The cosmic speed limit isn't about speed per se. It's about causality. It's about information. It's about the ability to cause effects. Everything that moves through space respects this principle. Everything that travels through the universe bows to this ultimate rule. And some of the most fascinating phenomena we'll explore next don't move through space at all. They don't travel from point A to point B. Instead, they grow, they expand. They swell outward in ways that blur the line between motion and growth, between traveling and becoming. This is where our mystery deepens. Because when you look at the cosmos, when you measure the velocities of distant objects, you find speeds that seem impossible. You find velocities that appear to exceed light speed. And yet, Upon closer inspection, they don't violate relativity at all. They reveal something even stranger. They reveal that space-time itself is expanding, and that expansion doesn't obey the rules that govern motion through space. Cosmic inflation's wild expansion. In the beginning, there was a moment so brief, so infinitesimal, that it barely deserves to be called a moment at all. This is the moment we call cosmic inflation. And during this moment, something happened that seems to violate every rule we've discussed. The universe expanded faster than light. Not light expanding into the universe. The universe itself expanding faster than light in all directions simultaneously. This happened about 13.8 billion years ago, in the first fraction of a second after the Big Bang. For the tiniest sliver of time, the universe was expanding at a rate that far exceeded the speed of light. In fact, the expansion was so rapid that it might be more accurate to say that the universe was doubling in size countless times per second. The numbers are so large they become almost meaningless. But the point is clear. Space itself was growing faster than light could travel. Now, you might think this is the smoking gun. You might think we've finally found something that moves faster than light. Einstein was wrong. The cosmic speed limit doesn't exist. But here's where the subtlety comes in, and it's a crucial one. Nothing was moving faster than light through space. Instead, space itself was expanding. And Einstein's rules don't apply to the expansion of space. Einstein said nothing can move faster than light through space, but he said nothing about how fast space itself can expand. It's a distinction that seems like a technicality, but it's actually profound. During inflation, if you were standing on a particular point in space and you measured how fast nearby objects were moving away from you, they'd all be moving slower than light. Locally, relativity was obeyed. But because space was expanding so rapidly everywhere at once, distant objects were receding from each other faster than light. The space between them was being created faster than light could traverse it. This is the key insight. Inflation didn't violate relativity because relativity governs motion through space, not the expansion of space itself. The universe found a way to expand faster than light while still obeying Einstein's cosmic speed limit. It did this by expanding space itself, not by moving objects through space. And the expansion was driven by something called the inflaton field, a quantum field that had an enormous amount of energy density. That energy caused space to expand exponentially. And then, nearly as suddenly as it began, inflation ended. The inflaton field released its energy, which became the matter and radiation that fills the universe today. And from that moment on, the universe expanded more slowly, governed by its density of matter and energy. Cosmic inflation is one of the most extraordinary phenomena in the universe. And it's a perfect example of how the universe respects the cosmic speed limit while still achieving seemingly impossible feats. The limit is real. It's absolute. But it only applies to motion through space. The expansion of space itself remains unbound. And in a very real sense, this expansion continues today. The universe is still expanding. And distant galaxies are still receding from us faster than light. But that's a story for the next chapter. Superluminal jets from black holes. Not far from the center of many galaxies, there are objects of such extraordinary power that they seem almost mythical. Black holes. And some of these black holes have jets of material shooting out from them at speeds that, when you first hear about them, seem to defy every law of physics. These jets move at speeds of up to 99.9% the speed of light. And when you measure them from certain angles, they appear to be moving at speeds greater than light. Scientists call this superluminal motion. And for a long time, it was genuinely puzzling. How could jets from black holes be moving faster than light? Didn't this violate relativity? Didn't this prove that something could exceed the cosmic speed limit? The answer is no, but the explanation is so elegant that it's worth exploring in detail. The illusion of faster-than-light motion comes from a phenomenon called relativistic beaming. Imagine a jet of particles shooting out from a black hole at 99.9% the speed of light. The jet is moving almost directly toward us, and as the jet moves, it's radiating light and other radiation. Now, here's the key. The jet is moving so fast that it's nearly catching up with the light it emitted a moment earlier. When the jet was at point A, it emitted a burst of radiation. Then the jet moved to point B, very close to point A, and it emitted another burst of radiation. From our perspective on Earth, these two bursts of radiation reach us almost simultaneously. We see the radiation from point B arriving almost at the same time as the radiation from point A. So when we measure the angular distance the jet traveled and we divide by the time it took for the light to reach us, we get an apparent superluminality. Speed. It's like the jet is moving faster than light. But the jet isn't moving faster than light. It's just moving so fast and in such a direction that the light from different parts of its trajectory reaches us in a compressed time frame. There's an additional effect called time dilation. Because the jet is moving at relativistic speeds, time moves slower for the material in the jet than it does for us. This further compresses the observed motion. But again, nothing is actually moving faster than light. We're just observing the light itself in a distorted way due to relativistic effects. This is why superluminal jets don't violate relativity, and it's why they're not evidence that faster-than-light travel is possible. The jets themselves are constrained to move slower than light. But the way we observe their light, due to relativistic beaming and time dilation, creates an illusion of superluminal motion. It's one of the most beautiful examples of how relativity can seem to produce paradoxes that dissolve upon closer inspection. The universe isn't actually breaking its own rules. It's just showing us that the rules are far subtler and more sophisticated than they appear on the surface. Observational illusions created by relativistic effects can seem to violate the cosmic speed limit, but the limit itself remains absolute and inviolate. The expanding universe. In the 1920s, an astronomer named Edwin Hubble made a discovery that would reshape our understanding of the cosmos. He was observing distant galaxies, and he noticed something remarkable. The light from these galaxies was redshifted. The wavelengths of light were stretched toward the red end of the spectrum. This meant the galaxies were moving away from us, and the farther away they were, the more redshifted their light was. The farther a galaxy was, the faster it was moving away. Hubble had discovered that the universe is expanding. And this expansion continues to this day. In fact, in the last few decades, we've discovered something even more startling. The expansion is accelerating. The universe isn't just expanding. It's expanding faster and faster. Distant galaxies are receding from us at speeds that seem impossible. Some galaxies are moving away from us faster than light. When we measure their recession velocity, we calculate speeds greater than the speed of light. How is this possible? How can galaxies move away faster than light? The answer is the same as it was with cosmic inflation. Galaxies aren't moving faster than light through space. The space between us and them is expanding faster than light. If you were sitting on a distant galaxy and you measured how fast nearby galaxies were moving relative to you, they'd all be moving slower than light. Locally, relativity would be obeyed. But because the universe is expanding, distant galaxies are being carried away from us faster than the speed of light. It's not motion through space. It's the expansion of space itself. And because relativity governs motion through space, not the expansion of space, there's no violation of the cosmic speed limit. In fact, this expansion provides us with a window into one of the deepest mysteries in physics. We know the universe is accelerating, but we don't know why. We've named the cause dark energy, but that's just a label for our ignorance. Dark energy is a kind of repulsive force that counteracts gravity. It pushes space apart, causing the expansion to accelerate. But we don't know what dark energy is. We don't know if it's a property of space itself, or if it's some exotic form of matter, or if it's a sign that we're missing something fundamental about gravity on cosmic scales. The expanding universe shows us that space itself is dynamic. It's not a static stage on which events occur. It's a living, growing, changing thing. And the expansion of space is one of the most profound phenomena in the cosmos. It connects cosmic inflation in the past to dark energy in the present. It shows us that the universe has a history and likely has a future. And it does all of this while respecting Einstein's cosmic speed limit, which applies not to the expansion of space, but to motion within space. The universe, it seems, has found many ways to be extraordinary while still obeying its fundamental rules. The speed of gravity. For a long time, one of the deepest questions in physics was whether gravity travels at light speed or instantaneously. Newton believed it was instantaneous. His equations worked as if gravity reached across space with no delay. But Einstein showed that gravity isn't instantaneous. It's the curvature of spacetime, and that curvature propagates at light speed. Gravitational waves travel through space like ripples on a pond, and they travel at the speed of light. But for over a century, this remained just a theory. We had no way to measure it directly. Gravitational waves are extraordinarily faint. The effect they have on the fabric of spacetime is minuscule. A gravitational wave from a colliding neutron star might stretch and compress objects on Earth by less than the width of a proton. Detecting such a tiny effect seemed impossible. But in the 1990s, physicists built an instrument called the Laser Interferometer Gravitational Wave Observatory, or LIGO. It's one of the most sensitive instruments ever created. 2 beams of laser light are sent down perpendicular arms that are 4 kilometers long. The beams reflect off mirrors at the end of each arm and return. If a gravitational wave passes through, it will stretch space in one direction and compress it in another. This changes the length of the arms infinitesimally. The laser beams will take slightly different amounts of time to return. And by measuring that difference, LIGO can detect gravitational waves. In 2015, LIGO detected its first gravitational wave. It came from 2 black holes colliding and merging together, billions of light years away, and the signal matched Einstein's predictions perfectly. The wave traveled at light speed. Gravity travels at light speed. Since then, LIGO has detected many gravitational waves. We've observed neutron stars colliding. We've created a whole new way of observing the universe. But more importantly, we've confirmed that gravity travels at light speed, not instantaneously. This has profound implications. It means that the universe's gravitational interactions are not instantaneous. When the sun moves, Earth's gravity doesn't respond instantaneously. It takes 8 minutes for the gravitational effect to propagate from the sun to Earth at light speed. Of course, because the sun is moving very slowly compared to light, we don't notice the delay. But it's there. Gravity, like light, like all carriers of information and causality, travels at the cosmic speed limit. And this provides us with one more confirmation that light speed isn't arbitrary. It's not just a rule imposed on particles. It's the speed at which the universe communicates with itself. It's the speed at which causes propagate to their effects. It's the speed at which information flows through the cosmos. And everything that carries information, everything that can cause effects, travels at or below light speed, gravity included. Grandfather paradoxes in spacetime. Imagine you could travel backward in time. Imagine you got in a time machine and journeyed back to 1945, and then you did something truly terrible. You prevented your grandfather from ever meeting your grandmother. Maybe you took him away before they could fall in love. Maybe you did something worse. Either way, they never met. They never had children. Your parent was never born. And if your parent was never born, then you were never born. But if you were never born, how did you travel back in time in the first place? You can't prevent your own birth. You can't travel to the past and erase the circumstances that created you. This is the grandfather paradox. And it's one of the most fundamental problems with backward time travel. The paradox reveals something profound about causality. Causality is the principle that causes precede their effects. You throw a ball at a window and the window breaks. The throw causes the breaking. It's not the other way around. Causality flows forward in time. It's one of the deepest features of our universe. And the grandfather paradox shows why backward time travel would be catastrophic. It would violate causality. It would create logical contradictions. It would allow effects to precede their causes. And this is where the cosmic speed limit comes in. Einstein showed that the cosmic speed limit isn't arbitrary. It's a consequence of how spacetime is structured. And that structure enforces causality. If nothing can move faster than light, then you can never have a situation where an effect precedes its cause. The light cone structure of spacetime, the boundary set by the cosmic speed limit, prevents such violations. You can only travel into the future. You can only move forward in time. You can't go backward. You can't create paradoxes. Some physicists have speculated about ways around this. Maybe you could take a closed time-like curve, a path through spacetime that loops back on itself. You could travel forward along this path, but the path would eventually bring you back to your own past. In principle, you could visit yourself at an earlier time. But here's the problem. Any attempt to use this path to create a paradox would require information or influence to travel faster than light at some point. You'd have to violate the cosmic speed limit to set up the paradoxical situation. And the cosmic speed limit, enforced by the structure of spacetime, prevents this. It's as if the universe is self-protecting. It won't allow you to create paradoxes. It won't allow causality to be violated. And the way it enforces this protection is through the cosmic speed limit. Nothing can move faster than light, because moving faster than light would allow you to create timeline paradoxes. The cosmic speed limit is therefore not just a rule about speed. It's a rule about causality. It's a statement about the fundamental logical consistency of the universe. And in a very real sense, the universe is built in such a way that causality must be preserved. Backward time travel would require exceeding the cosmic speed limit. And the universe won't allow that. Not because it's being stubborn, but because allowing it would create logical contradictions. It would make the universe incoherent. So the cosmic speed limit stands as a sentinel guarding the coherence of reality itself. The pole and barn paradox. Relativity creates some truly mind-bending situations. And one of the most famous is what physicists call the pole and barn paradox. Imagine a very long pole. It's 20 meters long. And imagine a barn that's only 10 meters long. Now, you're going to move the pole at relativistic speeds, at 90% the speed of light, directly toward the barn. As the pole moves faster and faster, it undergoes length contraction. Remember, objects moving at relativistic speeds appear compressed in the direction of their motion. At 90% light speed, the pole contracts to about 44% of its original length. So the 20-meter pole appears to contract to about 8.8 meters. Now, it's shorter than the barn. So here's the question. As the pole moves into the barn, will it fit? From the perspective of the barn, the pole is contracted to 8.8 meters, so it easily fits inside a 10-meter barn. The barn doors can close behind the pole without touching it. The pole fits entirely inside the barn. But now consider the pole's perspective. From the pole's frame of reference, it's not moving. The barn is moving backward at 90% light speed. And when you're moving at relativistic speeds, things in your direction of motion contract. So the barn contracts to about 440 meters. The pole is 20 meters long. The barn is only 4.4 meters long. How can the pole possibly fit inside the barn? This is the paradox. From the barn's perspective, the pole fits. From the pole's perspective, it doesn't fit. How can both be true? The resolution is beautiful and subtle. Both perspectives are correct, But the key is understanding what fits actually means. What matters is not whether the pole is shorter than the barn at some instant, but whether the pole can be entirely inside the barn at some moment in time in both reference frames. And the answer involves relativity of simultaneity. What counts as the same moment is different in different reference frames. In the barn's frame, there's a moment when the entire pole is inside the barn. The front of the pole reaches the far door, the rear of the pole is inside the barn, and the barn doors haven't closed yet. At this moment in the barn's frame, the pole fits. In the pole's frame, things are more complex. The barn is contracting, and it's moving backward. But there are also relativistic effects on the timing of events. When the barn's front door is open and the pole's front is at the door, events are happening at different times in the pole's frame than in the barn's frame. The resolution involves understanding that what counts as simultaneous is relative. Both observers are correct in their measurements. Both observers see the pole in different states of compression and the barn in different states of compression. But when you work through the mathematics of relativity carefully, the pole does fit inside the barn in both frames. It's not a violation of logic. It's not a paradox that reveals a flaw in relativity. Instead, it's a paradox that reveals how subtle relativity is. It shows that our intuitions about simultaneity and duration are wrong. It shows that space and time are woven together in ways that are far more intricate than our everyday experience suggests. The pole and barn paradox is a reminder that relativity doesn't break down. Instead, it reveals that the universe is far more elegant and self-consistent than we initially understood. The information loss paradox. Now we move into one of the deepest unsolved mysteries in theoretical physics. It involves black holes, quantum mechanics, and the very nature of information itself. In 1974, Stephen Hawking made a startling discovery. Black holes, which were thought to be purely black, purely absorbing, actually emit radiation. They leak energy. They slowly evaporate. This radiation is now called Hawking radiation. And it created an enormous paradox. Here's why. According to quantum mechanics, information is never truly destroyed. It might be scrambled, it might be hidden, but it's always there in principle. You could, in theory, reverse the process and recover the information. This is called unitarity in quantum mechanics. But black holes seem to violate this principle. When something falls into a black hole and passes the event horizon, it's gone. We can't observe it anymore. And if the black hole then evaporates through Hawking radiation, the information seems to be lost forever. If a black hole evaporates completely, all the information that fell into it is gone. You can't recover it. You can't reverse the process. This violates unitarity. It violates a fundamental principle of quantum mechanics. And this violation is the information loss paradox. For decades, physicists have grappled with this paradox. Is information truly lost inside black holes? Or is there some way that the information is preserved, hidden in the Hawking radiation, or encoded in some subtle way we haven't yet discovered? Stephen Hawking himself, late in his life, proposed that information might be preserved in a subtle way. But the paradox remains unresolved. What does this have to do with the cosmic speed limit? It's subtle but important. The information loss paradox arises because we have quantum mechanics, which says information can't be destroyed, colliding with general relativity, which says that everything inside a black hole is cut off from the rest of the universe. The event horizon is an absolute boundary. Nothing can escape it, not even information. These two pillars of modern physics seem to conflict, and the resolution might involve understanding how information propagates through spacetime in ways we haven't yet fully grasped. Some physicists think that the cosmic speed limit might play a role in resolving the paradox. If information is truly preserved in Hawking radiation, it must be preserved in a way that respects causality and the cosmic speed limit. The information can't escape the black hole faster than light. It can't propagate backward in time. It must find a way to emerge that respects the fundamental structure of spacetime. How it does this remains one of the great mysteries of modern physics. But it's a reminder that the cosmic speed limit isn't just an obstacle to overcome. It's a fundamental principle that enforces consistency in the universe. And any resolution to the information loss paradox will have to respect it. Reversing entropy's arrow. There's one more paradox I want to explore with you, because it connects to the cosmic speed limit in a surprising way. It's about entropy, about the arrow of time, and about why the past is fundamentally different from the future. If you've ever watched a glass of hot water cool down, you've witnessed the second law of thermodynamics. Entropy always increases. Heat flows from hot objects to cold objects, not the reverse. Energy disperses. Order becomes disorder. This is why you can unscramble an egg and make it whole again by reversing the process. You can't unscramble an egg. The universe tends toward disorder. This is what physicists call the arrow of time. The reason the past is different from the future is because entropy was lower in the past and is higher in the future. But here's a profound question. Could you violate the arrow of time? Could you reverse entropy? Could you create a situation where disorder becomes order, where cold things heat up at the expense of hot things, where eggs unscramble themselves? In principle, according to the laws of mechanics, yes. If you reversed the velocities of every particle in a glass of cold water, could reverse time. You could make it heat up. You could reverse entropy. You could unscramble the egg. But there's a catch. To reverse entropy on a macroscopic scale, you'd have to control the velocities of a tremendous number of particles with extraordinary precision. You'd have to process information about every particle. And to reverse the process, to undo the entropy increase, you'd have to communicate this information backward in time. You'd have to send signals faster than light. You'd have to violate causality. The cosmic speed limit prevents you from gathering the information necessary to reverse entropy on a macroscopic scale. The limit prevents you from creating time paradoxes. The limit prevents the future from affecting the past. And in doing so, it enforces the arrow of time. It makes the future fundamentally different from the past. It gives meaning to concepts like cause and effect, like irreversibility, like the flow of time itself. So even entropy, one of the most fundamental principles in all of physics, is ultimately enforced by the cosmic speed limit. The universe protects causality. It protects the logical consistency of reality. And it does this through the speed of light. Light isn't just fast. It's the fastest. And by being the fastest, it ensures that the universe remains coherent, consistent, and logically sound. The Alcubierre Drive. For as long as humans have dreamed of the stars, we've wondered how we might reach them. The nearest star to Earth, Proxima Centauri, is over 4 light-years away. Even traveling at 95% the speed of light, it would take you over 4 years to get there. And traveling at those speeds requires energy we don't have. We can't build rockets powerful enough. The physics seems clear. The stars are unreachable. Faster than light travel is impossible. But in 1994, a physicist named Miguel Alcubierre had an extraordinary idea. What if you couldn't move faster than light through space? But what if you could move space itself? What if you could contract space in front of a spacecraft and expand it behind, creating a wave of spacetime that carries the ship along? You wouldn't be moving faster than light through space. Instead, you'd be riding a wave of space that moves faster than light. There's a crucial difference. Einstein's rules say nothing can move faster than light through space. But they don't say anything about how fast space itself can move. This is the same loophole that cosmic inflation exploited. Alcubierre realized you could create a metric, a description of space-time geometry, that would allow this kind of motion. Inside the bubble of contracted space, you could be stationary relative to your local space-time. But the bubble itself would move through the surrounding space-time faster than light. From the perspective of distant observers, your ship would arrive at your destination faster than light could carry a message. But from your perspective inside the bubble, you'd never exceed light speed. You wouldn't experience any relativistic effects. You could reach the stars in arbitrarily short times. It sounds like the solution to everything. It sounds like the loophole we've been searching for. But there's a catch, a big one. To create such a bubble, you'd need exotic matter. You'd need material with negative energy density, negative mass, something that repels rather than attracts. As far as we know, exotic matter doesn't exist in usable quantities. We've never created it. We've never observed it in nature. And if it does exist, we have no idea how to harness it or produce it. The energy requirements are also staggering. Some calculations suggest you'd need more energy than exists in the observable universe to create an Alcubierre bubble large enough for a spacecraft. And even if you could create one, there are other problems. Hawking radiation might destroy the bubble. The quantum instabilities at the boundary might cause it to collapse. You might not be able to steer it or control it. The theoretical structure is sound. The mathematics works. The general relativity equations allow it. But the practical barriers are almost certainly insurmountable. The Alcubierre Drive remains in the realm of speculation, a beautiful dream that reveals the power of Einstein's theory while demonstrating its constraints. It shows us that faster-than-light travel isn't forbidden by the deepest laws of physics, but it's made so impractical, so energy-intensive, so dependent on exotic materials we've never found, that it might as well be impossible. The universe, it seems, is not keen on letting us cheat the cosmic speed limit, even through the most clever loopholes. Wormholes as shortcuts. Another dream that captured physicists' imaginations is the wormhole. A wormhole, sometimes called an Einstein-Rosen bridge, is a theoretical tunnel through spacetime. Imagine spacetime as a sheet of paper. Two distant points are far apart on that sheet. But what if you could fold the paper? What if you could bring the 2 points close together by folding spacetime on itself? A wormhole would be a tunnel through that fold. You could enter at one point, travel through the tunnel, and exit at a completely different location, light years away. You'd traverse the tunnel at normal speeds, slower than light. But because the tunnel is a shortcut through folded spacetime, you could cover vast cosmic distances in a short time. And from the perspective of distant observers, it would seem like you'd traveled faster than light. Wormholes exist as solutions to Einstein's equations. The mathematics is elegant. The geometry is fascinating. And they represent one of the most intriguing possibilities for faster-than-light travel. But again, there are enormous barriers. First, to keep a wormhole open, you'd need to support it with exotic matter, negative energy density, the same exotic substance you'd need for an Alcubierre Drive. Without it, the wormhole would collapse. The gravitational attraction on either side would pinch it closed. You'd need to actively maintain it, and the energy requirements would be enormous. Second, even if you could keep a wormhole open, traversing it might be impossible. The tidal forces inside might be so extreme that they'd tear you apart. The radiation inside might be so intense that it would incinerate you. Wormholes in realistic space-time geometries might be traversable in principle, but lethal in practice. Third, and perhaps most profoundly, we don't know if wormholes can actually exist in the universe. We've never observed one. We have no evidence that they form naturally. They remain mathematical constructs, solutions to Einstein's equations that might not correspond to anything real. Some physicists have speculated about microscopic wormholes, quantum foam structures at the Planck scale. But even if these exist, they'd be too small to traverse. You couldn't fit a spacecraft through them. And wormholes, like the Alcubierre Drive, point to a deep truth about the universe. The equations of general relativity allow for extraordinary possibilities. Curved spacetime, black holes, wormholes, shortcuts through space. But the universe seems to have safety mechanisms. It requires exotic matter, we can't find. It imposes energy barriers we can't overcome. It creates physical obstacles that prevent us from actually using these theoretical possibilities. The universe allows these exotic scenarios in its mathematics, but it does everything it can to prevent them from being practically useful. The cosmic speed limit stands not as an arbitrary rule, but as the consequence of a universe that protects itself. Closed, time-like curves. What if you could travel in a circle through spacetime? What if you could move forward through space and time in such a way that your path eventually looped back on itself? You'd emerge at your own past. You could meet yourself before you left. You could change events that have already happened. This is a closed time-like curve. It's a path through space-time that is closed, that comes back to its starting point. And it's allowed by Einstein's equations under certain conditions. In 1949, Kurt Gödel, the mathematician who proved fundamental limitations on logical systems, discovered a solution to Einstein's equations that contained closed time-like curves. Gödel's universe is rotating. In this universe, it's theoretically possible to travel in a closed loop through space-time and arrive at your own past. More recently, physicists have considered rotating black holes, wormholes, and other exotic space-time geometries that might permit closed time-like curves. The mathematics is sound. The geometry is feasible. But the practical and logical barriers are immense. First, there's the grandfather paradox, which we discussed earlier. Any attempt to create a time paradox through a closed time-like curve would require information to propagate in a way that violates causality. And creating that violation would require exceeding the cosmic speed limit somewhere along the path. Second, there's the question of consistency. If closed time-like curves are possible, then the past is not fixed. Events could be changed by information flowing backward through time. But this creates logical contradictions. How can an event happen if it's later changed by something that hasn't happened yet? Some physicists, like Igor Novikov, have proposed that the universe enforces self-consistency. If you travel back in time and try to create a paradox, something will always prevent you from doing so. The gun jams. The time machine malfunctions. A random quantum fluctuation intervenes. The universe adjusts itself to preserve consistency. This is the Novikov self-consistency principle. But it requires accepting that the universe has some form of intelligence or mechanism that prevents paradoxes. It requires believing that causality is not just a consequence of physics, but something actively maintained by the structure of reality. Third, and most fundamentally, we have no evidence that closed time-like curves actually exist in our universe. We don't observe any rotating regions of space-time that would permit them. We don't see evidence of time travel. We don't experience inconsistencies that would suggest the universe is rewriting its own history. The universe seems to be governed by a principle that makes closed time-like curves impossible. And that principle is the cosmic speed limit. By restricting the speed at which information can travel, by preventing effects from preceding causes, by enforcing causality, the cosmic speed limit prevents closed time-like curves from leading to paradoxes. It does this not through some external constraint, but through the very structure of space-time itself. The Casimir Effect. Sometimes the strangest physics comes from the most mundane observations. The Casimir Effect is a phenomenon discovered in 1948 by Dutch physicist Hendrik Casimir. It's peculiar, it's quantum, and it involves something that might sound impossible: negative energy. Imagine two uncharged metal plates placed very close together in a vacuum. According to the uncertainty principle, the vacuum isn't truly empty. Virtual particles are constantly popping into and out of existence everywhere. These virtual particles carry energy. They oscillate. They create a kind of quantum foam that permeates all of space. Now, between two closely spaced metal plates, only certain wavelengths of virtual particles can exist. The plates act as a boundary. Virtual particles with wavelengths larger than the separation between the plates can't fit between them. But outside the plates, virtual particles of all wavelengths can exist. This creates an imbalance. There are more virtual particles outside the plates than inside. The external pressure from virtual particles is greater than the internal pressure. The plates are pushed together. This is the Casimir Effect, and it's been measured experimentally. Two metal plates in a vacuum do experience an attractive force due to virtual particle pressure. But here's where it gets interesting. The Casimir Effect can be thought of as creating a region of negative energy between the plates. The energy density is lower between the plates than it would be in empty space. It's not negative in an absolute sense, but negative relative to the surrounding vacuum. And negative energy, as we've discussed, is exactly what you'd need to create an Alcubierre Drive or a wormhole. Could the Casimir Effect be harnessed? Could you use it to create the exotic matter necessary for faster-than-light travel? The answer, so far, is no. The amounts of negative energy produced by the Casimir Effect are tiny. They're far too small to be useful. You'd need to somehow amplify them, to concentrate them, to create a macroscopic region of negative energy. And we have no idea how to do that. We don't even know if it's possible. But the Casimir Effect shows that negative energy does exist in nature. It's real. It's measurable. It's not just a mathematical artifact. Which means that the universe isn't categorically preventing negative energy from existing. It's just making it extraordinarily difficult to produce in useful quantities. The universe seems to be playing a game with us. It's saying, yes, the mathematics allows for exotic possibilities. Yes, negative energy exists. Yes, wormholes and Alcubierre drives are theoretically possible. But the universe is vast, and the requirements are staggering, and the barriers are immense. If you want to achieve faster-than-light travel, you're going to have to solve problems that are far beyond our current capability. And by the time you're advanced enough to solve them, the universe might have aged enough that the cosmos will be unrecognizable. Why nature protects causality. As we've explored dream after dream of faster-than-light travel, a pattern has emerged. The mathematics allows for it. The equations of general relativity are flexible enough to permit Alcubierre drives, wormholes, and closed Timelike curves. But every time we get close to a practical solution, we run into barriers. Exotic matter that doesn't seem to exist. Energy requirements that are astronomical. Physical instabilities that would destroy the structure. Quantum effects that would prevent the journey. It's as if the universe is actively protecting itself. It's as if causality is so important, so fundamental, that the universe has built in multiple redundant safeguards to prevent it from being violated. This brings us to a fascinating hypothesis proposed by physicist Stephen Hawking. He called it the chronology protection conjecture. The idea is that the laws of physics, taken as a whole, will always prevent time travel and causality violations. Not because of any single law, but because of the collective effect of all the laws. Whenever you get close to creating a closed time-like curve, some quantum effect intervenes. Some instability appears. Some exotic requirement becomes impossible to satisfy. The universe, in other words, is self-protecting. But why should this be true? Why should causality be so fundamental that the universe protects it? The answer lies in the very concept of what makes a coherent universe. A universe without causality would be logically inconsistent. Effects could precede causes. You could change the past in ways that would create contradictions. The universe would be chaotic, incoherent, impossible. For a universe to exist at all, for it to have laws and patterns and consistency, causality must be preserved, and the cosmic speed limit is the mechanism by which this is preserved. By preventing information from traveling faster than light, by preventing effects from preceding causes, The cosmic speed limit ensures that the universe remains logically coherent. It's not just a rule. It's the foundation of reality's self-consistency. And in this light, the cosmic speed limit becomes something profound. It's not an arbitrary barrier imposed on the universe. It's a necessary condition for the universe to exist at all. It's what makes the universe a universe, rather than a chaos of contradictions. Every barrier we encounter when trying to achieve faster-than-light travel is an expression of this deeper truth. The universe is built to preserve causality. And because causality is preserved, the universe can exist. Neutrinos nearly break the record. On September 23, 2011, physicists at CERN in Switzerland announced something that shook the world. They had been firing neutrinos from Switzerland to a detector in Italy, a distance of about 730 kilometers. They were studying these ghostly particles, these almost massless creatures that pass through matter like it isn't there. Billions of neutrinos pass through your body every second, and you never notice. They barely interact with anything. But the neutrinos from CERN were special. They were moving fast, incredibly fast. So fast, according to the measurements, that they were arriving at the Italian detector faster than light could possibly travel the same distance. The announcement made headlines around the world. Faster-than-light particles discovered. Einstein might be wrong. The cosmic speed limit might not be absolute after all. But the truth, as is often the case in science, is more subtle and more interesting. The experiment was called OPERA, the Oscillation Project with Emulsion Tracking Apparatus. For months, physicists scrambled to understand how this could be possible. They checked the data. They looked for errors. Journalists speculated about the implications. Some physicists started thinking about how to modify relativity to accommodate faster-than-light particles. But then, in 2012, the OPERA collaboration discovered the problem. There were two mistakes in the experiment. First, a fiber optic cable connecting the GPS system to the timing equipment was loose. This introduced a timing error. Second, there was a problem with an oscillator used in the measurement. These small errors combined to create an illusion. The neutrinos weren't actually moving faster than light. They were moving at light speed, just like all massive particles that have been studied. The OPERA collaboration published a retraction, and physics returned to normalcy. But the episode is instructive. It shows how careful physics must be. It shows how even the most careful experiments can have hidden errors. It shows how the cosmic speed limit is so fundamental that we should be profoundly skeptical of any claim that it's been violated. The OPERA experiment was conducted with extraordinary precision. The measurements were performed by talented scientists, but they still made mistakes. And their mistakes were caught by the scientific community checking their work. This is how science works. We make claims. We subject them to scrutiny. We look for errors. And when we find them, we correct course. In this case, the cosmic speed limit was vindicated. Neutrinos, like all particles we've ever measured, respect the speed of light as an absolute boundary. Superluminal galaxies across the universe. When you look through a telescope at distant galaxies, you're seeing light that has traveled for billions of years. The light left those galaxies billions of years ago and is only now reaching Earth. And when astronomers measure the light from these distant galaxies, they notice something fascinating. The light is red-shifted. The wavelengths are stretched toward the red end of the spectrum. This is because the galaxies are moving away from us. The expansion of the universe is carrying them away. And the farther away a galaxy is, the faster it's receding. Some galaxies are so far away that they're receding from us faster than light. Their recession velocity exceeds the speed of light. When you calculate how far they are from us and how fast their light is red-shifted and apply Hubble's law, you get velocities greater than 300,000 kilometers per second. This seems impossible. Galaxies moving faster than light. But we've discussed this before. The galaxies aren't moving faster than light through space. The space between us and them is expanding faster than light. It's a subtle distinction, but it's absolutely crucial. Einstein's prohibition on faster-than-light travel applies to motion through space. It doesn't apply to the expansion of space itself. Space is allowed to expand as fast as it wants, and the expansion of space is currently accelerating due to dark energy. Measuring these superluminal galaxies was an important observation. It confirmed that the universe really is expanding. It showed us that distant galaxies are indeed receding at velocities greater than light speed. But it also confirmed a prediction of relativity. Expansion doesn't violate the cosmic speed limit. It's a manifestation of the cosmic speed limit in a different form. In Einstein's theory, spacetime is a single unified entity. Space and time are woven together. And the metric that describes spacetime, the mathematical object that tells you how to measure distances and durations, can expand. It can have expansion rates that exceed light speed without violating relativity. Observing superluminal galaxies, therefore, wasn't a violation of relativity. It was confirmation of it. It showed us that the universe is vast and expanding in exactly the way that relativity predicted. And it showed us that even at the scales of billions of light years, Einstein's theory continues to hold true. The Cerenkov radiation mystery. There's a phenomenon that occurs in materials that's so strange it seems to defy the cosmic speed limit. It's called Cerenkov radiation, and it involves particles moving faster than light. Imagine a particle moving through a transparent material, like water or glass. Light moves slower in water than it does in a vacuum. Light in water moves at about 75% of its speed in vacuum. But a charged particle, like an electron, can move faster than light does in water. It can move at 90% of light's speed in vacuum, which is faster than light moves through water. When this happens, something remarkable occurs. The particle is moving faster than the electromagnetic waves it's creating. It's outrunning its own light. And this creates a shock wave. Just like a supersonic airplane creates a sonic boom when it breaks the sound barrier, a particle moving faster than light in a medium creates a light boom. It creates Cerenkov radiation, and this radiation appears as a characteristic blue glow. You've probably seen Cerenkov radiation if you've ever looked at pictures from nuclear reactors. The water around the reactor glows with a blue light. That's Cerenkov radiation from charged particles moving through the water. Now you might think this violates the cosmic speed limit. A particle moving faster than light. But remember, the cosmic speed limit applies to motion through space. The particle is moving faster than light moves through water, but slower than light moves through vacuum. The cosmic speed limit still applies. Light speed in a vacuum, 300,000 kilometers per second, is still the absolute maximum speed for anything in any medium. Cerenkov radiation is a beautiful example of how the cosmic speed limit is about the speed of light in a vacuum, not about the speed of light in materials. Materials slow light down. But they don't change the fundamental cosmic speed limit. The limit remains. Nothing can move faster than light travels in a vacuum. And every observation of Cerenkov radiation confirms this principle. It shows us that even in the strangest materials and the most extreme conditions, the cosmic speed limit is respected. Gravitational wave detections. On September 14, 2015, two black holes collided. They had been orbiting each other for millions of years, spiraling inward due to the loss of energy through gravitational radiation, and then they merged. They became one. And in the violent instant of merger, they released as much energy as all the stars in the observable universe release in a year. All of that energy went into gravitational waves, ripples in the fabric of spacetime. These waves spread outward in all directions at the speed of light. And on Earth, 130 billion light-years away, they passed through us. They stretched and compressed space by an infinitesimal amount, and LIGO detected them. This was the first direct detection of gravitational waves, and it was a triumph of experimental physics. LIGO is an extraordinarily sensitive instrument. The two laser arms are 4 kilometers long. A passing gravitational wave changes the lengths of these arms by about 1 part in a billion. It's like measuring the distance to the nearest star to the width of a proton. That's the level of precision LIGO achieves. And when the gravitational wave from the merging black holes passed through, LIGO saw the signal clearly. The data matched Einstein's predictions perfectly. The wave had traveled at the speed of light. It arrived at Earth at the same time as the electromagnetic radiation from the merger would have, if there had been any. Gravity travels at light speed. This was a confirmation of something Einstein predicted in 1916, but had never been directly measured. It was also a powerful confirmation of the cosmic speed limit. If gravity could travel faster than light, the structure of spacetime would be different. Causality would be threatened. The universe would be unstable, but gravity travels at light speed, and this confirms that the cosmic speed limit is absolute. Since that first detection, LIGO and other gravitational wave observatories have detected dozens of gravitational wave events, merging black holes, colliding neutron stars. Each one confirms that gravity travels at light speed. Each one demonstrates that even the most energetic, most violent events in the universe respect the cosmic speed limit. Gravitational waves are some of the most direct evidence we have that the cosmic speed limit is real, fundamental, and inviolable. The Event Horizon Telescope's shadow. In 2019, humanity achieved something extraordinary. We took a picture of a black hole, not an indirect image, not an inference, but an actual photograph. The Event Horizon Telescope is not a single telescope. It's a network of radio telescopes spread across the world. They're synchronized by atomic clocks and operate as a single instrument with a virtual aperture as large as the Earth itself. By combining observations from telescopes in Hawaii, Arizona, Chile, Spain, Mexico, and other locations, astronomers created an image of unprecedented resolution. And they pointed it at Messier 87, a giant elliptical galaxy with a supermassive black hole at its center. The black hole is so enormous that it's about 3,000 times the mass of our Sun. It's surrounded by an accretion disk of hot, swirling material. And at the center, completely dark, is the event horizon, the point of no return, the boundary beyond which nothing can escape, not even light. What the Event Horizon Telescope captured is not the black hole itself, which is invisible. Instead, it captured the shadow of the black hole, the silhouette created by the event horizon blocking the light from the accretion disk behind it. The image was a perfect ring of light surrounding a dark center, and it matched Einstein's predictions with extraordinary precision. This was powerful confirmation of general relativity in the extreme gravitational environment of a black hole. It showed that Einstein's theory, which predicts the cosmic speed limit, continues to hold even in regimes of space-time curvature we could barely imagine. It showed that around black holes, where gravity is so strong that it warps space-time severely, the cosmic speed limit is still respected. The Event Horizon Telescope's success also demonstrated something about observation in physics. We can't directly see the event horizon. It's invisible by definition, but we can observe its effects. We can see the light from material orbiting near it. We can measure the gravitational effects on surrounding stars. We can build telescopes precise enough to see the silhouette. Through careful observation and clever use of physics, we can gather evidence about phenomena we can't directly access. This is how science progresses. We develop theories. We test them with observations. We refine the theories based on what we learn. And over, when we test the cosmic speed limit in the most extreme environments in the universe, we find that it holds. General relativity holds. Einstein's vision of spacetime, with light speed at its foundation, continues to describe reality with astonishing precision. The universe, it seems, is built on principles that are far more fundamental and far more elegant than we initially understood. Light speed as a fundamental truth. We've journeyed through relativity and quantum mechanics. We've explored black holes and the expansion of the universe. We've looked at paradoxes and dreams and the experimental confirmations of Einstein's vision. And through all of this exploration, one theme has emerged again and again. The cosmic speed limit isn't arbitrary. It's not a rule that happens to constrain the universe. It's fundamental. It's woven into the very fabric of what spacetime is. Think about what light speed really is. It's not just the speed at which photons travel. It's the speed at which the electromagnetic force propagates. It's the speed at which gravity propagates. It's the speed at which changes in any field propagate through space. It's the speed at which information can travel. It's the speed at which causes become effects. In Einstein's formulation, light speed emerges naturally from the mathematics of spacetime. It's the maximum speed at which events can be causally connected. It's the speed at which the metric of spacetime, the mathematical object that describes distances and durations, becomes singular. At light speed, time stops. Space contracts to zero. Light speed is the boundary of what's physical and what's not. And here's the profound part. This speed is the same everywhere. It doesn't depend on the motion of the observer. It doesn't depend on the intensity of the light or the distance it travels. Light speed in a vacuum is 300,000 kilometers per second, always. This constancy is what makes relativity possible. This constancy is what forces us to re-examine our concepts of simultaneity and duration. This constancy is what makes time relative and space relative and mass relative. But light speed itself is absolute. Everything else bends to accommodate it. And this tells us something deep about the nature of reality. The universe is not built on a stage of absolute space and absolute time, as Newton thought. The universe is built on a stage of space-time, in which space and time are woven together. And the constant that governs this space-time is light speed. You could say, in a very real sense, that the universe is built from light. Light speed is the fundamental constant around which all of physics is organized. All of relativity emerges from it. All of quantum mechanics must be compatible with it. All observations we make confirm it. There is no known exception to it. And perhaps most importantly, there is no reason to expect an exception. The cosmic speed limit isn't a temporary rule that might be superseded by a deeper theory. It's a consequence of how space and time are structured. It's a feature of the arena in which all physics takes place. And any future theory of physics, even if it replaces relativity or quantum mechanics, will have to respect this fundamental truth. The universe is built on light speed. The universe's self-consistency. Imagine a universe where causality could be violated, where effects could precede their causes, where information could travel backward in time. What would such a universe look like? It would be chaos. It would be logical contradiction. If you could change the past, then what was the past? If you could cause an effect before its cause occurred, then what is the distinction between past and future? Such a universe would be incoherent. It couldn't have laws. It couldn't have predictability. It couldn't have meaning. For a universe to be coherent, for it to have physical laws that don't contradict each other, causality must be preserved. Causes must precede effects. The past must be fixed. The future must be open. And the cosmic speed limit is the mechanism by which this is preserved. By restricting how fast information can travel, by preventing effects from preceding causes, by enforcing causality, the cosmic speed limit ensures the universe's internal consistency. It's like a cosmic immune system, protecting the universe against logical contradictions. And this perspective shifts how we think about the cosmic speed limit. It's not a constraint imposed on a pre-existing universe. It's a necessary condition for the universe to exist at all. Without the cosmic speed limit, without causality, without the restriction on information flow, there would be no universe. There would be no laws. There would be nothing. The cosmic speed limit is therefore not something the universe obeys reluctantly, constrained by external laws. It's something the universe obeys because obeying it is what makes the universe a universe. Every time a physicist discovers a new loophole, every time they find a way that seems to violate the cosmic speed limit, they eventually realize that the violation is only apparent. The reality is more subtle. Information isn't actually traveling faster than light. Causality is being preserved. The universe is protecting itself. This is not a coincidence. This is the universe being self-consistent. It's the universe protecting its own logical foundation. And this brings us to a philosophical realization. The universe isn't governed by external rules imposed by some higher authority. The universe governs itself. The rules of physics are not constraints on the universe. They're descriptions of how the universe must be in order to exist. And the cosmic speed limit is the foundational rule from which all others emerge. It's the principle that makes logical consistency possible. It's the principle that makes causality real. It's the principle that makes meaning possible. Think about this for a moment. You exist because the universe has laws. The universe has laws because it must maintain internal consistency. It maintains internal consistency because it enforces causality. It enforces causality through the cosmic speed limit. In this chain of reasoning, light speed is not just fundamental to physics. It's fundamental to existence itself. What this tells us about reality. Over the course of these 3 hours, we've asked a simple question. Is anything faster than light? And through our exploration, we've discovered that the answer is far more interesting than a simple yes or no. Yes, there are phenomena that seem to move faster than light. Cosmic inflation, expanding galaxies, entangled particles, virtual particles, tunneling electrons. But none of them actually violate the cosmic speed limit in a way that would allow information to travel faster than light or causality to be violated. And this teaches us something profound about the nature of reality. Reality is not simple. It's subtle. It's nuanced. It's far more clever than we initially imagine. The universe doesn't just say no to faster than light travel. It says yes in ways that ultimately preserve the cosmic speed limit. It finds loopholes that aren't really loopholes. It permits paradoxes that collapse upon inspection. It shows us that beneath the apparent complexity of the universe, there's an elegant, self-consistent, logical structure. And that structure is built on the cosmic speed limit. This tells us something about how science works. Science is not a process of discovering rules imposed on the universe from outside. Science is a process of discovering how the universe is structured, how it's built, what it fundamentally is. And what we've discovered, through centuries of careful observation and theoretical development, is that the universe is built in a very specific way. It's built so that causality is preserved. It's built so that information cannot travel faster than light. It's built so that effects follow causes, always. The universe is not random. It's not arbitrary. It's coherent. It's self-consistent. It makes logical sense, and the cosmic speed limit is the expression of that logical coherence. This also tells us something about the future of physics. There may come a day when we replace Einstein's theory of relativity with a deeper, more fundamental theory. We may discover that general relativity is only an approximation of something more comprehensive. We may find new phenomena, new laws, new structures that we haven't yet imagined. But whatever replaces relativity will have to preserve causality. It will have to respect the cosmic speed limit. It will have to maintain the logical consistency of the universe. Because these are not contingent features of reality. They're not accidental. They're necessary. They're fundamental to what it means for the universe to exist. And finally, This tells us something about the human condition. We live in a universe built on causality. We live in a universe where the past shapes the future. We live in a universe where our actions have consequences that propagate forward in time. The cosmic speed limit makes this possible. It makes choice meaningful. It makes time real. It makes our existence in the universe something more than a random collection of particles. We are made of particles that respect the cosmic speed limit. We are creatures of causality. We live in the arrow of time. And that's not a limitation. That's a gift. That's what makes existence possible. The future of the search. As we near the end of our journey, I want to look ahead. Where is physics going? What new mysteries are we about to encounter? What new challenges to the cosmic speed limit might emerge? The truth is, we don't know. But we can make some educated guesses based on the puzzles we're currently trying to solve. One of the biggest unsolved problems in physics is reconciling general relativity with quantum mechanics. Einstein's theory works brilliantly at large scales. Quantum mechanics works brilliantly at small scales. But at the scale of black holes, where gravity is both strong and acting on quantum systems, the two theories conflict. They give contradictory predictions. A successful theory of quantum gravity, a theory that unifies relativity and quantum mechanics, might reveal new structures in spacetime. It might show us that, at the smallest scales, spacetime is not continuous. It might be granular, built from discrete units. This theory might reveal new loopholes or new confirmations of the cosmic speed limit. Another frontier is dark matter and dark energy. We know these mysterious substances make up 95% of the universe, but we don't know what they are. Understanding dark matter and dark energy might require new physics. It might require modifications to relativity or quantum mechanics. It might reveal new cosmic speed record holders. Yet another frontier is the nature of time itself. We still don't fully understand why time has a direction, why the past is different from the future, why we remember the past but not the future. A deeper understanding of time might also be a deeper understanding of causality, and that might shed new light on the cosmic speed limit. Finally, there's the possibility of discovering phenomena that we haven't even begun to imagine. In the history of physics, whenever we've looked at the universe at a new scale or with new instruments, we've found surprises. X-rays and gamma rays and radio waves and gravitational waves. Every time we've expanded our ability to observe, the universe has shown us something unexpected. Perhaps there are phenomena even faster than light speed waiting to be discovered. Perhaps there are new forms of causality or new structures of spacetime that we haven't conceived. The future of physics is not predetermined. It's open. It's an unfolding story. But one thing seems certain. Whatever we discover, whatever new laws we uncover, whatever new phenomena we observe, the cosmic speed limit will be there. Not as an arbitrary rule, but as an expression of something even deeper. The universe is built on causality. The universe is built on logic. The universe is built on consistency. And those truths will endure, long after Einstein's equations are superseded, long after quantum mechanics is replaced, long after we've solved all the mysteries that currently perplex us. The cosmic speed limit might change in form. It might be expressed differently, but it will remain, because without it, there would be no universe at all, and with it, all things are possible.